Hello and welcome to BCM325 Future Cultures and this lecture on Artificial Intelligence, Predictions and Revolutions. In this lecture, I'm going to be drawing on the work of Spyros Makridakis, the director of the Institute for the Future at the University of Nicosia in Cyprus. Makridakis is a professor of decision sciences and a leading expert on forecasting with multiple books and articles on the subject. I'm going to focus on two articles he wrote, which features predictions about the future of technology. The first, from 1995, called The Forthcoming Information Revolution, Its Impact on Society and Firms, published in the journal Futures, and his follow-up article in 2017 from the same journal called The Forthcoming AI Revolution, Its Impact on Society and Firms. These two articles, 22 years apart, are a useful means for reflecting on the impact of the industrial, the digital, and the information revolutions in terms of how they inform the way we make sense and make predictions about the potential for an AI revolution, particularly in terms of the changes in technology, society, and culture that may occur in the next 20 years. While there are many predictions about AI from scientists, technologists, and entrepreneurs like Stephen Hawking, Bill Gates, Elon Musk, and Ray Kurzweil, there are also just as many predictions from corporations, governments, and agencies currently working on developing and regulating these technologies. I'm also going to link to a couple of articles which cover some of these predictions in the details below. This lecture is going to focus on the differences between the future as seen from 1995 and 2017, and conclude with 4 types of attitudes or scenarios that Makridakis argues are common in predictions about technology, especially artificial intelligence. It's important to remember that the very rapid speed of technological innovation means that predictions tend to date very quickly. It's also important to keep in mind that there is a difference between types of artificial intelligence, from complex algorithms to machine learning and neural nets, and what's referred to as full general intelligence, much like that of a human. I'm not going to spend a lot of time on these differences. If you're new to AI, a great place to start and get a general overview is the Wikipedia page on AI. One of the main functions of science fiction, particularly the science fiction texts that we're examining in this subject, is to get an understanding of how artificial intelligence has been represented in popular culture and the gap between how we imagine AI in terms of interactive computers, robots, and androids, and the reality of AI, which has primarily been based on automation and algorithm. However, remember that the point of science fiction is not to accurately predict the future, but to help imagine the future into being. I've previously covered this point in the video lecture in this series on science fiction. Makridakis' first prediction article from 1995 envisioned the forthcoming changes that would result from the information revolution at a time when steady progress was being made in computer processing speeds, chip design, and digital storage. This table, taken from the 2017 article, is an updated summary from the 1995 article of the significant inventions from the industrial, digital, and forthcoming AI revolutions. One of the critical concessions to take away from all of this is the self-admission that Makridakis did not predict 2 of the most important innovations in the last 20 years, the internet and smartphones. He did, however, predict the convergence of technologies from multiple devices to single devices capable of multiple functions. He imagined a computer that would be useful for watching movies and TV, shopping and banking, medical and health, video games, accessing news, teleconferences, learning and education, as well as other services, which is everything that the mobile smartphone technologies made possible. He just didn't imagine it in that form. This suggests that predictions do not necessarily need to be exact in order to help us understand how technological change might have implications for social and cultural change and vice versa. If you're interested in this, I highly recommend Martin Hilbert's video unpacking the difference between technological determinism and social constructivism, or the social shaping of technology, which is linked in the details below. Looking back at 1995, many of the technological affordances that we take for granted today were pure science fiction then. It might sound mundane to you now, but accessing online libraries of scientific articles and downloading the latest research, rather than scouring through print journals, is totally amazing to anyone like myself who had to spend countless hours photocopying articles for later use as an undergraduate student. At the time, science fiction movies like Johnny Mnemonic, Hackers, and The Matrix, as well as books like William Gibson's Neuromancer and Neil Stephenson's Snow Crash, imagined the internet as a fully embodied and immersive virtual world, whereas the reality is simply 60 trillion web pages, 2.5 billion smartphones, 2 billion personal computers, and 3.5 billion Google searches a day, that is somehow both much more amazing and simultaneously much more banal. What we see from Makridakis' 1995 paper is the dual nature of prediction, that where there is accuracy, that accuracy often manifests in unexpected ways. Take, for example, the way he predicted that wireless telecommunications will be possible and accessed from anywhere in the world without the need for regular telephone lines, which, although accurate, doesn't specify the affordability and the commonality of smartphones, that by 2015 would be as powerful as the most expensive 1995 supercomputer, allowing for countless applications, platforms, services, and other innovations and activities that were totally unimaginable in 1995, or at least if they were imagined, it was in the speculative realm of science fiction. By looking at the historical trends from the industrial and digital revolutions, Makridakis was able to predict that automation would lead to robotic factories and the elimination of repetitive manual tasks. We see this in bookkeeping and budgeting, as well as mail sorting and complex calculation. But he was unable to foresee the widespread success of the internet, the power of search engines and recommendation algorithms, the reshaping of the media industries, digital currency, and the rise of the gig economy, as well as the power of social networking, all enabled by the availability, desirability, and people's use of smartphones, and of course the related telecommunications infrastructures. All of this is important for thinking about AI, particularly in terms of its impact on the media and communication industries, not merely because AI will obviously exist, but how societies, cultures, and individuals will make sense of, regulate, experiment with, and integrate AI into their daily lives. What we see often is movies that are very dystopian and series like Black Mirror that kind of reveal the nightmare associated with this kind of technological integration in our lives. But I think, as we can see from history, the reality is largely unimaginable because it's ordinary. The future is probably going to be much more ordinary than what we currently imagine it will be. It's also important because both wrong predictions and partial predictions are still useful. A leading technologist in the 1980s and 1990s for Microsoft and founder, of course, and CEO, Bill Gates, was famously wrong about the internet. He was completely wrong about users. He was totally misguided about open access and imagined that email spam would be eradicated within 2 years, even though now in 2020, it's still the most sent mail type on email. Although the best quote and the best wrong quote from a Microsoft CEO was Steve Ballmer's prediction in 2007 that there's no chance that the iPhone is going to get any significant market share. Makridakis quotes another great wrong prediction from J.B. Say, a French economist writing about cars in 1828, who said, "Nevertheless, no machine will ever be able to perform what even the worst horses can, the service of carrying people and goods through the bustle and throng of a great city." Specificity is a core trap for prediction. To realistically imagine the future of technological advancement and innovation, particularly in terms of artificial intelligence, means that we have to look at historical and current trends, but realize that innovation is not necessarily linear. At a cursory glance, the rapid expansion of technological development appears exponential. However, it is not just the raw speed and power of technologies, or the reduction in the time and cost of development of new technologies, but rather their diffusion, affordability, reception, and application by users that is important. Here's a series of examples. There were 200 years before the creation of Newcomen's steam engine in 1708 and Henry Ford's reliable and affordable, for the time, Model T automobile in 1908. There was 90 years between the commercial availability of electricity and its extensive use in factories to increase productivity. There were 20 years between the creation of ENIAC, the electronic numerical integrator and computer, which is generally considered to be one of the first electronic general-purpose computers in 1945, and the release of IBM's mass commercial system in 1965. There were 10 years between Dr. Martin Cooper's first mobile telephone call and the first commercial mobile phone launch by Motorola in 1983. And only 2 years between the introduction of internet-enabled smartphone technologies in 2002 and significant new innovations and affordable products offered by Samsung. There now exists a very minimal delay between innovation and introduction to the market, thanks to the availability of rapid prototyping and rapid production facilities in places like Shenzhen in China. New developments in machine learning, algorithmic analysis, and other artificial intelligence applications for things like speech and facial recognition, text prediction, image analysis, internet search, and other apps, platforms, and services are being rolled out globally across smartphone infrastructure almost immediately. There is, however, a significant difference between the automated machines of the Industrial Revolution, the computers of the Electronic and Digital Revolution, and the coming effects of the Artificial Intelligence Revolution by orders of extreme magnitude, because the goal for AI is not merely greater automation and higher computational power, but the human-like ability to learn from experience. That may sound a little anticlimactic, but in reality, the idea that a machine can learn just like a human or a non-human equivalent is truly profound. It's a huge ambition with paradigm-changing implications. Makridakis provides a useful example to think about the difference between machines, computers, and AI. The ubiquitous thermostat. A thermostat is a basic but powerful cybernetic machine because it exhibits a highly valuable type of intelligence, the ability to seek equilibrium. Once set with a temperature, a thermostat will activate cooling or heating, or both, to bring about the room's temperature according to its predetermined setting. Computers are an advanced iteration of the same principle. They are calculation machines that use logic-based rules and decision trees to produce the exact same result every time. This is one of the fundamental features of a computer, that every time it completes a computation, the answer is exactly the same. Today, computers operate at incredible speeds, but they are totally limited to predetermined programming. True artificial intelligence is not going to be restricted by predetermined results because it has the capacity to learn and adapt. One of the early examples of this was the neural net device from 1990, which was created to read handwritten digits on bank checks. Because things like numbers on checks and addresses on envelopes and parcels can have an almost infinite variation due to handwriting, they required an entirely new kind of programming to understand them. I remember in the 90s in Australia when Australia Post introduced this technology, and it actually had a dramatic improvement on the speed of letter and parcel delivery. Other advances in the 1990s included the robot Polly that could learn to pronounce words, and the robot Asimo, which could navigate basic open spaces. In 1997, the supercomputer Deep Blue was able to analyze 60 billion chess moves in about 3 minutes in order to defeat chess grandmasters. Deep Blue, however, was a hard number-crunching machine and similar to the Watson supercomputer, which won the game show Jeopardy in 2011. Watson's victory was mostly a result of the speed of calculation and information retrieval. However, its programming was able to make sense of clues, word associations, puns, and questions framed in natural language, as well as learning from past mistakes, which contributed to a real leap forward. In 2015, the computer program AlphaGo successfully beat a human professional player at the game of Go, board game that is exceptionally popular in East Asia. AlphaGo Zero went on to win a string of victories, including one against the #1 ranked player of Go in Korea in 2017. Created by DeepMind Technologies, which was later purchased by Google, AlphaGo uses the Monte Carlo tree search algorithm to determine moves that it has learned from playing against itself, other computers, and human opponents in the past. Using a neural network structure, it can predict successful moves and represents a huge step forward in teaching machines to be creative and improvise solutions to problems. But instead of mimicking a human, and particularly the human strategy to maximize gains, AlphaGo takes a more holistic approach, a distinctly non-human approach, and seeks to maximize the probability of reaching a winning position. This has important implications because the ultimate goal is not to make a computer that thinks like a human, but an artificial intelligence that can learn in its own way. The next step for AI, like AlphaGo, is to be able to make decisions in situations where the rules are not set. When Makridakis first wrote his predictions back in 1995, it was only 2 years after the introduction of the groundbreaking Intel Pentium processor. The Pentium was a highly successful brand of CPU for desktop personal computers because it had a number of features, including the integrated processing of improved graphics and sound quality. Intel had made speed and architectural innovations that would be built on for more than 20 years. Leading to the current generation of game consoles, mobiles and portable devices, robots, supercomputer systems, and of course, self-driving cars. In the next 20 years, leaps in technological progress will be equally transformative and lead to entirely new types of entertainment, healthcare, education, manufacturing, design, and so on. But not necessarily because of innovations in the design of computers or computational speed, memory sizes, or similar types of improvements in architecture, but through programming and software that is capable of acquiring knowledge through trial and error, adapting, and even being creative. It may not be long until entire games, movies, television, comics, books, news, current events, teaching and learning systems, even architectural designs and engineering designs are being entirely created by artificial intelligence systems. We're already seeing examples of where machine intelligence is being used to create art, music, literature, and film scripts. According to Forbes, media organizations like the New York Times, the Associated Press, Reuters, the Washington Post, and even websites like Yahoo Sports are already using AI to generate news content. DeepMind has had success with its neural program that is able to beat early video game classics like the Atari 2600 system by teaching itself how to play without instruction, merely learning through trial and error. That AI has now moved on to much more complicated strategy games like Blizzard's StarCraft, and this has implications for the future of not only video game competition, but video game design. Inspired by these successes, governments, corporations, universities, and other organizations around the world have invested billions in AI research, much of it based on deep learning approaches, which are often limited by the massive amount of data and information resources that are needed for the neural networks to train themselves on. In 2019, we saw several apps based on forms of facial recognition that were very popular. Ones that included taking a photo of your face and then making you look like a baby or an old person, or mapping your face into famous scenes from movies so that you look like the star of the movie. These had the added benefit of creating an enormous database of human facial images and captured sound recording of human natural speak. These are being used to train the next generation of facial recognition software and human-machine interaction apps. While there still exists massive inequality, devastation, and suffering globally, it is undeniable that the revolutions of the industrial and information ages have increased the standards of living, employment, health, education, and provided a range of significant benefits to societies and cultures around the world. The question is whether the coming AI revolution will continue or radically alter this trend for the worse or the better. Makridakis suggests that the critical question is, what will the role of humans be at a time when computers and robots perform as well or better and much cheaper practically all tasks that humans do at present? He suggests that there are 4 common scenarios that attempt to answer this question at present. Let's start with the pessimists. Elon Musk, CEO of Tesla and SpaceX, is a famous AI pessimist, concerned with the possible negative consequences of AI. Musk has gone on record saying that AI is like summoning a demon, with consequences potentially worse than nuclear weapons. He is not alone. Writing in Wired magazine in the year 2000, Bill Joy suggests that our most powerful 21st century technologies, robotics, genetics, engineering, nanotech, are threatening to make humans an endangered species. This is an extreme but not uncommon reaction to AI because, like Joy, many believe that as artificial intelligence becomes more of a reality, societal problems become more complex. I think we can see this play out in terms of Facebook and YouTube and its recommendation algorithms and the associated politics. As intelligent machines gradually take over making the kinds of decisions that humans have previously been required to make, the unintended consequences will begin to manifest and magnify. This will make humans even more dependent on machines and pushed outside of critical decision-making processes in the everyday entirely. Although, looking at the job we're currently doing, this might not be a bad thing. The automation of decision-making by machine intelligence can be observed in terms of the algorithmic content moderation on platforms like Google, YouTube, Facebook, and Instagram. These algorithms have important consequences for many individuals whose livelihood depends on machine learning networks not making mistakes over their content in terms of appropriateness and advertiser friendliness, but more especially copyrighted material, especially where there are powerful corporations with multiple layers of obfuscation, denial, and difficulty in the appeals process. In his book, Homo Deus, A Brief History of Tomorrow, Yuval Noah Harari discusses 3 critical concerns for the future of humanity. 1. The understanding of life as data processing units and the treatment of all organisms as algorithms. He suggests this is more than just dehumanizing, but the reduction of life to thinking machines and the implication of unrestricted utilizing and exploitation of all data processing units. 2. The decoupling of intelligence from consciousness and the valuing of intelligence over consciousness. For example, the Google search algorithm, the Amazon recommendation engine, and the Facebook newsfeed algorithms. Currently, these assist us in finding what we think we want, but they do not assist in helping us to understand the consequences of those recommendations or evaluate their effects. And 3, the likely occurrence that non-conscious algorithms will know us better than we can know ourselves. This is the concern over the implicit values programmed into algorithms by humans that do not necessarily have our personal values and interests in mind, such as self-driving cars. These might be able, and probably will be able, to make better and faster decisions than human drivers overall. But what if they are predetermined to put the safety of its occupants ahead of pedestrians or animals? This is another example of the technological determinist argument versus the understanding of the effects of social decision-making on the reality of the impacts of new technologies. Only in conjunction with governments will automatic cars be allowed to become widespread. And it will be legislators and people that will decide on the conditions under which self-driving cars will be able to operate. For example, it may be decided that yes, while AI can operate vehicles, by law, there has to be a human present in an oversight capacity. This will have safety and insurance implications, as well as help to mitigate labour displacement for the hundreds of millions of truck and bus drivers, couriers, post deliverers, and other transport industry workers. It is, however, likely that over time, more and more artificial intelligence machines and algorithms will be tasked with taking over jobs usually performed by humans, which brings us to the pragmatist view. Pragmatists, like Sam Altman and Michio Kaku, the author of the 2018 book The Future of Humanity, believe that open AI technologies, controlled by effective regulation, will ultimately benefit humankind and the world as a whole. John Markoff puts AI into two categories, one being the attempt to duplicate human abilities, and the second being the augmentation of human abilities. The second is more pragmatic and practical, particularly in the short term, as it expands on the trajectory of the machine, electronic, digital, and information technological revolutions. Just as the steam engine, the telegraph, the computer, and the mobile phone expanded human capacity, AI will greatly augment human ability. Rather than replace humans entirely, the future is likely to benefit, particularly in the next 20 years, from AI and human partnerships. Working in conjunction with AI, the human-AI team will be greater than the AI or humans working separately. The pragmatist view is that humans can regulate and work with AI. They can regulate AI through hardware and software limitations, through legal means, as well as social and cultural practice to minimize the danger that AI poses and maximize the benefits in their augmentation of ourselves. This brings us to an important category, the doubters. The doubters are a category or a response or view of AI that thinks that AI, and particularly general artificial intelligence, is pure hype, an exciting and interesting science fiction novum, but an impossibility that will never ever be as real as popular entertainment or these futurists like to imagine, and therefore it's not going to be a threat to humanity. One of the most famous doubters in his book, What Computers Still Can't Do, a critique of artificial reason in 1972, Hubert Dreyfus famously concluded that the majority of predictions about machine intelligence fail to manifest. Similarly, Jankel wrote in the Huffington Post in 2015 that AI will never be able to achieve the heights of human creativity and innovation, that there will always be a gap between AI and the types of creative, empathic, risk-taking, and entrepreneurial decision-making abilities of the human. This brings us to the final scenario, the optimists. Famous inventor, innovator, and predictor of the future, Ray Kurzweil suggests that computers will reach general human intelligence around the year 2029, while the singularity, the runaway point of technological growth resulting in machine superintelligence far superior to that of humans, will occur by the year 2045. Optimists like Kurzweil believe that this will initiate a new golden age of prosperity for humanity, in which any technology imagined by humans can be developed by our superintelligent AI, creating a series of new revolutions in genetics, nanotechnology, robotics, space travel, education, philosophy, and beyond. They imagine that age, disease, inequality, environmental degradation, all of these would be solved and left behind as humans become a post-human species working towards a utopia for all. Of course, the pessimist counter to the optimist is that optimists greatly overestimate the technical challenges to reach general AI and the singularity, but also significantly underestimate the dangers that these developments possess, especially the potential for a new order of class division to occur between those in control of AI and those regulated to second-rate status, or even worse. There you have it. What do you think? Which category or scenario do you think is most likely, and why? I really do recommend taking a look at both Madridakis articles from 1995 and 2017, which are available on the Subject Learning site. And I'm going to conclude now where Madridakis begins with a quote from Stephen Hawking, which is entirely pragmatic. The rise of powerful AI will either be the best or worst thing ever to happen to humanity. We do not yet know which. So remember, the future is now.